Today we have Dr. Pooya Hamdi from the Aachen University. He's senior research engineer and scientist in the Aachen University, and he's working with the reservoir mechanical research group in some of the exciting fronts in 3D printing and rock mechanics, and you will see some of that next week. And with Dima, a PhD student from Aachen University, also visited us here. With that, I think just to say that Dr. Pooya's research really is focused on rock mechanics, physical modeling, and numerical modeling related to slope stability, landslides, and tunneling, and also in geological repositories, which is the topic that we're going to see today. Without more further ado, please join us.
Thanks a lot.
Thank you.
Thanks, Gonzalo, for the kind introduction. Good afternoon, everyone. It's my pleasure to be here. So today I'll be talking about a project that we have started 2 years ago, where you're going to look into construct a new underground research laboratory similar to what was constructed 20 years ago in Canada, in Manitoba. The focus of this research is try to look into brittle fracturing applied to nuclear waste repository. So today it's going to be a general overview of what we have done, what we are planning to do, and a little bit of introduction in terms of nuclear waste repository and high-level nuclear waste. So as Gonzalo said, I'm a senior scientist in RWTH University in Aachen. But I got my PhD in Canada in 2015 in Vancouver. I was doing my PhD with Professor Dr. Stedt at Simon Fraser University. And during that work, my focus of the PhD was trying to understand brittle fracturing at various scales using numerical modeling. And since then, I tried to expand my research. And when I was putting together the slides, I realized that I'm basically working on 3 different categories. We can name it as the different sizes. We have micro scale, laboratory scale, tunneling scale, and larger scale, which is slope stability and landslides. As Gonzalo said, we've been working with GeoPrint and U of A on a project called 3D printing that Dima is going to be presenting it next week. This is the project that we started last year. And the focus is going to understand the brittle fracturing pattern using 3D printing and consequently use numerical modeling, try to calibrate the results. And from medium scale type of project, I work a lot on tunneling. PRECODE Project is the project that I'm going to introduce today in this presentation. But on top of that, I'm also involved in a really nice project called Einstein Telescope, which we are trying to find the best location to host the 3rd generation gravitational wave detector in Europe. And also Monterey, another underground research laboratory for nuclear waste in Switzerland, and a bit of pet projects and R&D projects in yielding support element. And from slope stability landslide, we have a couple of projects. One is in Alaska, which immediately after this visit, I'm flying to Alaska. Here we are looking at the impact of deglaciation and global warming on landslides and how the rock is moving as a result of deglaciations. So a bit of everything. But as I said, today I will be talking a bit about nuclear waste repository and a brief introduction of the PRECODE projects in Switzerland. So I'm quite sure that you're familiar with the whole concept of nuclear waste repository, but I decided to put a couple of background information to make sure that everyone is on the same page. So obviously, when we have nuclear waste power plants or nuclear medical clinics, at the end of the day, we are producing nuclear waste. And nuclear waste has to be disposed at the end of their lifetime. And depending on how severe the nuclear waste is in terms of their half-life, decay, radioactivity, and the amount of heat that they emit during this disposal, we can categorize them into 3 different groups: low, intermediate, and high level. And one of the most common way of disposing intermediate to high-level nuclear waste is deep geological repository, which is basically trying to construct a tunnel below the ground, generally speaking 400, 500 meters below the surface, and then dispose them safely using different barriers. On the left-hand side of the slide, we see a Swedish/Finnish concept of high-level nuclear waste repository, where you have the number one as the host rock. If I can bring up the pointer. So you have the host rock as the last barrier, and you have the bentonite. And obviously, this is the tunnel that we have constructed. And here is the vertical concept to be able to put the canister. And this to the right is the horizontal concept for nuclear waste repository. So essentially, what we have is a series of pillars that are hosting our nuclear waste. And then you have a copper or steel barrier as a second barrier. You have the bentonite as a third barrier. And at the end, you have the host rock as the third barrier. So for the nuclear waste to escape from the area, it has to go through different barriers. And what we are looking at as a geological engineer is to understand the behavior of the last barrier, which is the host rock itself. Here's a nice picture that I've taken from Bossart. He was the head of Monterey Underground Research Laboratory in Switzerland, showing the evolution or possible evolution of the high-level nuclear waste from the day that we construct the repository all the way when we get to the qualitative equilibrium, which we get to the point that the nuclear waste is not going to be harmful anyway. And if you look at from the time, you're actually talking about 1 million years from now. So when we are talking about the long-term behavior of the host rock in nuclear waste, we're actually talking about a really, really long time. So the definition of time is quite variable depending on the disciplines. But here we are talking about 10,000 or 100,000. That we want to make sure that the structure is going to be stable. Starting from the lower portion, it takes about 10 to 100 years until all the induced stresses that we've caused or we've introduced to the domain as a result of shaft sinking, as a result of tunneling, access sealing, and then emplacement of the bentonite takes to equilibrate. And then after that, we just leave it abandoned. And then automatically through the natural process, we start having the equilibrium in terms of the temperature between the canister and also the host rock. And then this temperature starts reducing as the time passes. In a Swiss standard for opalinious clay, sedimentary rock, we've been expecting that the amount of heat transport between the canister and the bentonite, and obviously from bentonite to the rock, is going to be about 90 to 100 degrees. So here, what we are trying to analyze is a thermal, mechanical, and hydraulic type of coupling, because all these three components are playing a key role here. So mechanical, understanding the mechanical behavior is just one side of the story. It has to be hydro-thermomechanical. And then after about 10,000 years, we get to the point that we are gradually equilibrating into a qualitative equilibrium. So unlike a lot of countries, Germany hasn't decided which host rock they're going to go for. As a general introduction, we can go for clay rock, we can go for salt, and then we can also go for crystalline rock. For example, in Canada, right now there are quite a lot of research on limestone and granite. So the mine by experiment in Manitoba was purely on crystalline rock. Switzerland has already made a decision. They're going to go for opalinious clay. They've already finalized the location of the nuclear waste repository. The same for Finland and Sweden, that they have gone for the crystalline rock because probably that's the only rock that they have there. But Germany has all three options. So they have salt areas for salt, crystalline rock, and clay material. That's why we've been asked to do some research to be able to better understand the long-term behavior of the crystalline rock. And to be able to speed up the whole process, we could be able to have an underground research laboratory in Switzerland, which the host rock is pretty much similar to what we can expect in Germany for crystalline rock. So if I want to give you a quick overview of what we are looking after, this is a really famous chart for underground excavation from Hook, that basically, depending on the rock mass strength, if you start from the left-hand side of the chart to the right-hand side, imagine that you're increasing the amount of fracturing or basically reducing the strength of the rock mass. And if you move from the top to the bottom, you're increasing the in situ stress. It could be moving from the shallow tunnel all the way down to a deep tunnel. And then we can expect a different variety of the behavior. And we get to the point that depending on how strong the rock is, you're moving towards brittle fracturing in a case that the amount of stress is high enough to cause some new induced fractures. It's always a battle between strength and stress. And let's say for a certain rock, in this case, for more than 1 kilometer of Petretto, rotondo granite, we get to the point that we are causing some induced fractures. That's why it becomes really important to understand this type of fracturing pattern, because what we don't want for nuclear waste is to create new fractures that can be able to the new radionuclide be able to escape from the canisters itself. So to be able to understand the short-term, medium-term, and long-term behavior of the brittle fractures are quite important. And in the past few years, mostly because of the technologies that we have available, we start understanding more and more about brittle fractures. So what it means is that now we can go deeper, much deeper than we used to go in terms of tunnels, in terms of block caving in the mining environment. And this has caused a lot of challenges and of course a lot of understanding of the brittle fracturings, because as we go deeper, the stress is going to get higher and higher, and we get to the point that the rock is not able to sustain the stress, and then we start having fractures around. A really nice example is what we have on the left-hand side, Gotthard Base Tunnel, which is the largest and longest railway tunnel in the world, passing through mountainous area of Switzerland, about 57 kilometers. And as you can see, it's going through different types of rocks. I can bring up my pointer. It's passing through different types of rock and obviously different level of overburden, to the point that at certain part, let's say Zethum and Fido, they were getting really close to 2.5 kilometers of overburden. And there is no rock that can sustain that much of stress without producing any fracture. On the right-hand side is the Grasberg mine. This is the project that I was involved before I go to Germany. And as you can see, the mining is started from the open pit on the top, and then they get to the point that they couldn't go any deeper with the open pit, and then they realized that there is a lot of ore bodies, copper and gold, still there. So, and the only option that you can have is to go block caving or stock-level caving in general. And to give you a sense of size, here we are looking at 1 kilometer. So there was another probably 1 kilometer, 1.5 kilometers that they can go deeper to be able to extract all the ore bodies. And again, what we are having is a series of tunnels, which are definitely going to go through the brittle fracturing and induced fractures. From stress analysis perspective, before we start tunneling, obviously we have initial stress. It could be a isotropic stress, could be normal faulting condition, meaning that the vertical stress is high and the horizontal ones are the intermediate and minimum principal stress, or it could be opposite reverse faulting where we have the horizontal stress to be the largest and the intermediate one. And depending on the amount of in situ stress that we have, the location of the stress concentration, the maximum compressive strength changes. So in this case, where we have the horizontal stress to be the maximum, the stress concentration for most compressive stress is going to be on the roof and the floor. And if we have the normal faulting condition, what we end up having is a stress concentration in the sidewalls. And basically, this dictates where we are going to have the excavation damage. So understanding this stress is really important. When we start talking about spalling and rock bursting, a lot of learnings that we have, a lot of things that we do know are actually coming from the underground excavation, the underground research laboratory, particularly in Canada. On the picture on the right-hand side is one of the snapshot of a tunnel in URL, Manitoba, that the plan was to construct a circular tunnel, but what they ended up having was a V-notch shape in the roof and the floor, about 1.3 times higher than the actual radius of the tunnel. And the reason that it's a little bit tilted is that we have the major principal stress a bit tilted from horizontal. That's why this V-notch shape is not completely in the roof and the floor. And again, from nuclear waste repository perspective, what we don't want is to having a uncontrolled brittle fracturing that we cannot be able to predict. What's happening in crystalline rock, which are generally massive, is that we have, this is a schematic illustration of generally what happens in the massive crystalline rock around the tunnel in the area that we have the maximum compressive strength. If there is going to be a little bit of micro cracking, not even a completely fully persistent discontinuities, because of the stress concentration around the tunnel and unconfined condition, what we end up having is a potential for crack initiation, particularly at the tip of these micro cracks. And as these fractures are getting bigger, they might reach to each other, creating large fractures. And then what we end up having is a really onion skin slabs of rock, and then they cannot be able to sustain the load anymore, and then they pop out of the sidewall. And this procedure repeats itself until we get to a self-equilibrium into the tunnel where the amount of confining pressure is a bit higher to be able to prevent it. A couple of slides or a couple of snapshots from different tunnels showing different level of spalling and rock bursting. And here is a TBM, and you have a really onion skin fractures that are running parallel to the tunnel itself. It could be in a millimeter scale. It could be in a centimeter scale where you start having a really, really large slabs falling from the tunnel, or it could be a complete overbreak in a meter scale. That the initial idea was to having a horseshoe-shaped tunnel, and all of a sudden you have a really huge overbreak. So when we are dealing with brittle fracturings, it could be either rock spalling, which is a non-violent development of the fractures, and it's generally it takes a bit of time to develop rock spalling, and then it's a self-stabilizing system, meaning that as soon as you get to the point that the confining pressure into the tunnel is sufficient enough, it stops. A couple of snapshots here, you can clearly see that slabs of rock is being away from the tunnel itself, and then we get to the point that they end up falling into the ground. And here is a really nice example of what we saw in a pressure tunnel in Switzerland, that it was just at the beginning of development of the spalling itself, and it was in a millimeter scale. The problems that we can run into is obviously when we are excavating the tunnel with TBM, the gripple itself cannot be able to push against the wall to go ahead. You end up having a really, really soft and unsupported material that cannot be able to sustain the amount of torque that is required for the TBM to go forward. A really nice example is a tunnel, a pressure tunnel in Switzerland that we visited last year. And to give you a sense of how critical the Spalling becomes for TBM, is that here there was a pressure tunnel, so there was a 700 meters of elevation gain here, and the tunnel was going horizontally up to this stage and going 60 degrees upward, between 45 to 60 degrees upward. So the whole procedure from here to the top was using TBM. Just imagine that the TBM is trying to go up, and then this is the gravity is pushing it down. And what they end up having in this case, they can be able to play it. Doesn't have the. So what we were trying to do here was that we were on the top of the locomotive, and then with the normal geologic hammer, we were just trying to bang on the wall. And you can what hopefully you can be able to hear is that you hear a really hollow sound of rock as I'm pushing the. And what was happening was that the spalling was developing around the tunnel, and the TBM was going 45 degrees to 60 degrees upward. And now all of a sudden you have the wall that is not sustaining any load anymore. So, and in a normal horizontal tunnel, it's not a big deal. We can hopefully can go with it. But when you have a 60 degrees, 45 degrees upward TBM, the gravity is not really helping. So if you have really spalling, you're going to have really big problems. And what was happening here was that they start putting a lot of cable bolts as soon as the excavation was done, wire mesh, to be able to prevent this spalling to develop. Here's a example of a really severe spalling and rock bursting. Definitely what we do want to be a basic question. And what is happening here is that the amount of stored energy is so much, and the rock is so brittle that as soon as it becomes unstable, it just completely piece of rocks fall from the ground itself, to the point that it can clearly destroy all the support system that it can have. Another example of the rock bursting. That was a tunnel in Switzerland, in Fido station, where again what you end up having is a really sudden violent failure of the brittle fractions. In a ductile material, the development of the deformation is so slow, you can be able to see the deformation is happening. You end up having a lot of deformation, so to the point that the tunnel can collapse, but at least we can be able to see. Here, everything is just so sudden with the release of energy. So what is happening generally for spalling is you have the maximum stress acting around the tunnel, depending on the in-situ stress, and then they start developing these micro cracks, and then they get to the point that the dilation happens, the spalling and slabbings, and then the process continues itself to the point that you get to the stage that the amount of confining pressure that is acting in this direction is sufficient enough to prevent it from happening. That's why for Ritum pressure tunnel, what was recommended was immediately put the wire mesh, because a little bit of confining pressure can stop the procedure itself. And then here's a catalog of spalling, completely non-violent, all the way to strain bursting with a lot of overbreak itself. So as you can see, I think there is a lot of quite familiar names from Canada. Mark Dietrich is from Queen's University. There is quite a lot of slides from Professor Derek Martin from U of A. And a lot of learnings came from the underground research laboratory in various countries. As I said, there is a lot of country collaborating with each other to find the best location and geologic setting for intermediate high-level nuclear-based repository. On the left-hand side is the Monterey Underground Research Laboratory in Switzerland, in Open clay. We have the ASPO Hard Rock Lab in Sweden, in crystalline rock, the AECL URL in Manitoba, Canada. And then to the right one is the Onkalo facility in Finland, which this is going to be the first tunnel that you're going to actually dispose the nuclear-based repository. So what we see over there to some extent is the underground research laboratory. And in this area is the underground research laboratory, but here is actually a development of the nuclear-based repository itself. So Finland, the same for Sweden, they have decided to go for crystalline rock. Here is a couple of snapshots from the URL in Canada, courtesy to Professor Martin. And what we end up seeing again, if I want to show you what has been done over there in a really quick way, it was underground research laboratory at two different levels, 240 and 420. So in 240 level, everything was pretty much uniform. The amount of stress was dictated by amount of overburden that we had. But in 420, there was a locked-in stress, and the amount of in situ stress was significantly higher than what was in 240 level, to the point that the amount of horizontal stress was around 65 megapascal, causing a lot of induced fractures in various shapes. And here's an example of how the V-notch shape looked like in a larger scale, and this is how the procedure is going to look like in a smaller scale. Here we are probably looking at 10 centimeters of a snapshot here. A lot of learning that we are adopting for our project is actually coming from all the existing underground research laboratories. So with that, a couple of slides about what we are planning to do. The project is called PRECODE. It stands for Progressive Excavation Disturbance Zones Evolution During and Post-Mine by Tunneling. So what we are trying to do in this project is to understand the brittle fracturing in situ at smallest, in short term, during the excavation, medium term, 1 or 2 year after the excavation, and then the long-term monitoring. It's a collaboration between RWTH University, us in Aachen, ETH Zurich, York University, and Dalhousie from Canada. And the project is funded by BGE, which is the federal agency controlling where the nuclear waste is going to be disposed in Germany. A bit of setting about the Brittle tunnel. The PRECODE tunnel is going to be excavated within the existing Brittle tunnel. So in 1984, during the construction of the Furka base tunnel, that you can see the cross section of that, This is one of the most important railway tunnel in Switzerland. They have decided to build Bedretto tunnel, about 5.2 kilometers long, to be able to transport the excavated material from Furka tunnel out to the Bedretto Valley and be able to transport it out. So what we have inherited, or what ETH has inherited, was a possibility of using this existing Bedretto tunnel to be able to do research. There is a lot of research happening in Bedretto at the moment, to some extent regarding the geothermal energy and also nuclear waste repository and fault activation as well. So if we take a cross section here, what we have is that, as you can see, the amount of overburden goes up to about 1.7 kilometers of overburden. And the location that we would like to put our PRECODE tunnel, which I'm going to show you in the next slide, is about 2,400 TM tunnel meter. And the amount of overburden is going to be around 1.2 to 1.4 kilometers. The host rock, as we pass through the portal, we get to the rotundo granite, which is a homogeneous crystalline rock with a really high amount of uniaxial compressive strength, about 200 megapascal of in situ stress, of the uniaxial stress. Location, here is Switzerland, here's the Bedretto tunnel. This is the Italian province of Switzerland, and then we are pretty much close to Italian border, about 1 hour drive to the closest city in Italy. What we have observed is that as we pass through the tunnel, as the amount of overburden increases, we can see clearly a sign of spalling on the existing Bedretto tunnel. So we know that the amount of stress that is acting there is quite in our favor of spalling. It's below the strain bursting, which is good for us because we can have a controlled deformation. And it's beyond the crack initiation level. That's a really good setting for us to be able to do our tests. So what we are planning to do is to combine lab scale type of experiment that's generally done by York University and Dalhousie University, to some extent by us. A detailed in situ monitoring for a section of the tunnel to be excavated, and obviously numerical modeling. So it's going to be a really iterative process of data collection, lab testing, and verification using numerical modeling. And the hope is to be able to understand the short-term, medium-term, and long-term behavior of the rotundo granite for sake of a nuclear waste repository. So the in situ monitoring part on its own is quite comprehensive. We have been putting a lot of effort so far to be able to optimize our monitoring system, which is encompassing a series of different approaches. Seismic monitoring, we have active and passive seismic monitoring. We are using a lot the fiber optics and distributed acoustic sensing and distributed strain sensing. And these are the technologies that weren't available 20 years ago, and it's becoming more of a routine for research. And on top of that, we are monitoring in really high detail hydraulic behavior of the tunnels with hydraulic tomography with our Packer, mini Packer system, as you can see on this side. So it's basically a portable device with different Packer system that we can isolate a section of the tunnel and then start injecting and understanding the permeability of the host rock. And if the permeability is changing over time, it means that the fractures are developing. And then we also have geophysical monitoring, P-wave and S-wave velocity, optical and acoustic, televiewer, continuous time lapse of the fracturing, GPR or ground penetrating radar, basically non-destructive or non-invasive type of monitoring. We have a series of deformation monitoring, both in the boreholes and along the tunnel. We're using the laser scanning on a regular basis, and obviously the fiber optics to be able to have a really micro scale monitoring of the deformation for a couple of boreholes that we have. And on top of that, we have monitoring boreholes for stress measurement and environmental measurement. And the unique setting for Bedretto is that the relative humidity is high and the temperature is also varying, so we can also see what's happening as we perturbate the environmental impact, temperature and relative humidity, which happens to be a really important factor for development of the brittle fracturing. This is how it looks like in a snapshot for PRECODE tunnel. So we have the existing Bedretto tunnel, and then you would like to have a 10-meter of the side tunnel using drill and blast, and then about 11 meters of what we call it soft excavation. Here it used to be called line drilling and rock splitting, which is nothing but drilling a series of radial boreholes around the perimeter of the tunnel, and then try to use the rock splitter to remove the rock from inside. And the main reason, this is a snapshot of the underground research laboratory in Canada, in Manitoba, where they adopt this type of excavation. And the whole purpose of having this type of excavation rather than a normal drill and blast is to minimize the impact of excavation method. If you have drill and blast, no matter how controlled it is, you're causing some fractures. And what you're monitoring later on, you don't know whether it's coming from the excavation itself or is it coming from the stress redistribution. So this is going to be one of the best approaches in terms of mechanized excavation to minimum the impact of excavation method in those fractures. And then after that, we have a series of boreholes in terms of in longitudinal version and also radial version. And then after that, we have about 100 meters of drill and blast tunnel for purpose of different projects. So what we have done so far is the pre-existing Bedretto tunnel provides us a really nice playground to understand the brittle fracturing after 40 years. Because, as I said before, the tunnel was constructed 40 years ago. So now we have a snapshot of brittle fracturing 40 years after the construction of the tunnel. Even though the tunnel was excavated using drill and blast, it still tells us a lot about how and what we can expect from the tunnel itself. On the right-hand side, the video is showing a really detailed textured point cloud using the laser scanners, where we can be able to get a good sense of the amount of overbreak and the deep and deep direction of the structures, their aperture. And we are going to use this type of method, remote sensing in general, to be able to get a time lapse of the fracturing in the Bedretto or PRECODE tunnel. And on top of that, we have done a series of geophysical testing, GPR, and then gas permeameter on the wall, and also some borehole measurement using our MMPS or mini modular packer system to get a sense of micro cracking inside the tunnel itself. What we found was that here is a snapshot of one of the permeability measurements. So we have the permeability as a function of borehole depth. Just imagine that 0 is at the wall, and then 1.5 is 1.5 meter into the wall. So what we can clearly see is that even after 40 years, after all these slabs of rock spalled from the tunnel itself, we can clearly see increase of permeability close to the wall, and then going back to ambient or the initial permeability as we go deeper into the ground itself, which is quite unique. It shows that at the beginning, we have a lot of overbreaks, larger structures, and that is already spalled off from the tunnel, but we still have a lot of micro cracking as a result of the stress-induced fractures. We also did a series of lab testing. Here is an example of the gas permeability test. Here as a function of borehole depth. Again, a similar observation at laboratory doing the permeability test using the portable gas thermometer on the borehole itself that has been obtained from the borehole itself. The other thing that we have been working on a lot is to understand the crack initiation, crack damage level at laboratory scale. It's been found that for brittle rocks, as soon as you go beyond the crack initiation level, which is generally about 30 to 50% of the ultimate peak, you start having macro cracks. So the fractures starts to initiate in the sample. And then as you increase the stress, it might get to the point that you have crack damage level about, let's say, 80 to 90% of the UCS, where all these fractures coalesce and create the larger structures. From nuclear waste repository or long-term strength of the rock, the crack initiation level is really important. That's why we put a lot of effort to understand at which level we end up having the crack initiation level. Here is an example of what we have done. A rotunda granite as a sample with a lot of acoustic emission sensor attached to it to be able to get a sense of acoustic emission counts and also event location and moment tensor analysis. What we found was that here the black one is stress, axial stress versus axial strain in horizontal axis. And then the orange one is the acoustic emission counts. We can be able to clearly find the crack initiation level and crack damage level, both using the strain monitoring and also acoustic emission monitoring. In our case, the crack initiation for that specific sample was around 40% and crack damage around 80% of the UCS. And the amount of stress that we expect after tunneling for bedretto is beyond the crack initiation level. So we can be able to expect to have spalling around the tunnel. I think this is going to be my last slide. On top of that, what we have done is try to calibrate the model as we go. So basically, the more data becomes available, it allows us to do numerical model. Here is a simple example of what happens in terms of spalling or brittle fracturing around the tunnel if we change the crack initiation level. So obviously, here we have a crack initiation of 50 megapascal all the way to 70 megapascal. And as the crack initiation level gets higher, we expect to have a significantly less spalling and rock bursting. And this type of information allows us to fine-tune our orientation of the boreholes, especially for monitoring, because right now we are assuming that the excavation damage zone is going to evolve around the sidewall of the tunnel, meaning that the vertical stress is the maximum stress. But the stress in bedretto is a bit heterogeneous depending on how close to the fault you are, and then all these type of catalog of the results allows us to be able to modify last minute the configuration of the boreholes if we realize that the stress is going to be different. Here we are looking at two different scenarios in terms of hydraulic conductivity and how the core water pressure dissipates over time. And again, this type of behavior and analysis allows us to fine-tune our core water pressure monitoring test kits. So where we are at the moment is that if I go back in terms of what we have done, right now we are excavating the logistic niche, which is a widening of the existing bedretto tunnel to allow us to bring machineries. And then hopefully 1 month from now, we're starting with the borehole drilling, all these longitudinal boreholes, and after that, the drill and blast and the soft excavation. So we are hopeful that by the March or April next year, we can be able to be at this stage, which by that time we start monitoring from day one. So all the longitudinal boreholes are going to be drilled and instrumented before the drill and blast comes, so we can be able to have the data from day one of the excavation itself. And then lab testing, we also sent a series of samples to York University, and they're planning to do the lab testing. And as the data becomes available, we're going to go with the advanced numerical model itself. And I think with that, thanks a lot. And here's the reference, and we will be happy to answer the questions.
Thank you.
If in the rock salts,
Yeah.
if you look at it, this is just a really snapshots of the pros and cons of each of these geologic settings. I start from crystalline rock, which I'm more familiar with. It's low permeable material. It's super strong and super brittle, but doesn't have the self-healing and self-sealing properties. The fracture is there; it remains there. Whereas it's not the case for clay material and salt material. Clay material has self-sealing behavior. At Monterey, there is a super nice illustration of the water column. It's a column that you have a little bit of Opelina's clay in between, and there is a water over there. And they had this snapshot of that. As soon as it comes in contact with water, you have this self-sealing and spalling, and then all of a sudden the water stays there. And just think of it as water as right now nuclear waste. Salt has self-healing process. It heals itself. It deforms, but at the same time, it has this potential of healing itself. So as soon as the fracture is there, over time, it heals itself. But this is the positive part. The disadvantage is, as you said, it's creeping. It has time-dependent component. The time-dependent component of that is totally dependent on the amount of differential stress and the temperature, right? But if you can be able to predict, if you can be able to minimize the differential stress, and also take into account the temperature differences that is going to be there, you can also be able to manage it. But right now, the majority of the countries, as far as I know, are either towards the crystalline rock or clay, or sedimentary rock in general, clay or limestone. It depends on, well, it totally depends on which borehole you're talking about. But you're all in the, I'll go back here. So we have HQ and NQ, 72 mil of diameter, 48 of diameter, and 101 of diameter. So the one that I was showing you here, millimeters, yeah. Yeah. 101 millimeter. 101. 101.
Okay, yeah.
No, 101 is 10 centimeters. This is the 10 centimeters. This is one of the largest one. And then we have NQ and HQ, 48 and 72 millimeter. No, just bear in mind that if you want to go with this diameter, obviously the bigger the better, but you need to have a significantly strong and stiff machine to be able to break it. The UCS of this one is 180 megapascal. That's a lot. So obviously, the bigger the size, the higher the load has to be, right? But so far, our experience is that the amount of size difference in terms of diameter is not really impacting it, at least for the range of the test that we are doing for granite, homogeneous granite. Homogeneous intact, yeah. The grain size of these rotunda granite are not significantly big, so even smaller diameter can give us reasonable and logical results. No problem.
Very quiet order the department president working in granite comments. Permeability testing.
Not yet, but this is something that we are going to look at the moment. This setting was a bit, we wanted to go with the lateral strain control type of testing to make sure that we get the post-peak really nicely. Then we realized that for the setup that we have, we cannot be able to go lateral strain, and then we switch from lateral strain control to axial strain control. That's why at the beginning it's a little bit odd, but we are definitely looking into that. We still trying to analyze these the event location, because with the number of AE sensor that we had, it allows us to also do the event location. This is still work in progress for us.
So, with respect to the DDR, how high the heat transfer how this increase in temperature affects your pore pressure, and I wonder if this pore pressure is affecting also the excavation zone.
To your question about temperature, it depends on the concept itself. I think here I had the concepts, the concept from Switzerland in Ophiolinius clay, and the heat transport between canister and bentonite from the rock is around 90 degrees. And they have a in situ testing for, they call it FE fault, FE experiment, which they have a complete replica of. I think probably what I have here as a demo is exactly what they have in reality. So they have put the canister obviously without nuclear base, but a lot of temperature sensor around it, and they have the bentonite and the tunnel itself, and there are a series of boreholes around the whole system, both in the bentonite and the host rock itself, monitoring pore water pressure, strain, temperature. And with that, they are hopeful that they can be able to understand the pore pressure impact. But coming back to your question, obviously change of pore is a fully coupled process. So change of the temperature changes the pore water pressure, and obviously mechanics, and then you can just go mechanics change the pore water pressure and temperature itself.
One more question.
We do need to have, that's probably I'm not the best person to answer that question, but I think we need the amplifier. Within it's a customized acoustic emission sensor for us with the ceramic inside. And I think it has the amplifier. But from in situ monitoring, we have a series of amplifier here. I think if I go back to the slides. Here we have AE receivers and transmitter, and some of them we have amplifier as well. Yeah. No, it's a customized one because for the borehole ones, I don't think, well, probably you see here, I don't know how to what detail. It has the curvature of the wall itself to make sure that we have the maximum coupling. So probably this one, I don't know to what detail you see. It's a AE that is a clamp that push against the wall. This is the in situ one I'm talking about. And then it has the curvature of the borehole wall to maximize the amount of coupling. It's pushed against. Yeah.
There's one question for me there on the permeability test between with the air, the granite. Is there any consideration to other tests?
This one was just a prototype of what we have developed with a colleague of us in Japan. This is a really portable device that allows us to do, maybe I'll just go here again. So here is a portable device, and the whole idea behind this one is that it's fast and we can get the screening of the entire permeability on the wall. I don't know if you see here, you have all these glues that allows us to put the tip and then quickly get a rough permeability of the material using gas. But on top of that, we have, probably this is the best one. So we have one pore water pressure monitoring that is running at an inclined angle to the excavated tunnel, and there is going to be 3 different pore water pressure monitoring. And the whole idea behind this one was we wanted to see to what extent the pore water pressure halo changes as the excavation is happening. So we have one pressure monitoring away from the tunnel, which probably the impact is going to be seen later in time. And we have one pore water pressure monitoring here, or sensor here, that is going to be close to the tunnel. So things are going to be seen ahead of time. And then on top of that, we have 2 twin boreholes, or 1 twin boreholes that we would like to have our MMPS. And here, what we have is that, just imagine that we have another MMPS here, and we are isolating this interval, this interval, this, and this. And then it's a modular system. We can be able to pack up 25 centimeters close to the wall or away from the wall. And then we would like to do a systematic injection over time. So we have a time lapse of permeability. And if we see the change of permeability over time, it means that fractures have developed. And it could be a good sign about the brittle fracturing around the sidewall of the tunnel. And on top of that, we have, where is it? We also have on top of that, maybe this is going to be there if it goes back. Yeah. So on top of that, we also have this radial borehole where we have multiple fiber optics. So we can be able to see the deformation, look at how it looks like in pore water pressure, and on top of that, we have acoustic emission sensor. So, and then on top of that, we have geophysical modeling on the surface. So we are hopeful that we can have, for a smaller scale, a good understanding of what is happening in the tunnel, both using seismic, geophysical, hydraulic, and mechanical.
Thank you for